Have you ever stood outside on a quiet evening, watching the last colors of the sunset melt into the deep blue of the night sky, and felt a sense of wonder about just how far those colors have traveled to reach your eyes? Light is so common that we almost never think about it, but it is one of the most mysterious and magical things in the entire universe. It moves across billions and billions of miles of empty space. It carries messages from stars that died long before the Earth was born. It lets you see the face of someone you love from across the room. It allows doctors to see inside the human body without a single cut. And hidden deep inside this simple, everyday thing is a secret that changes everything we know about time, space, and reality itself. This is the story of light. This is the story of its speed. And this is a journey we will take together, very slowly, so you can relax, let your mind drift, and enjoy the quiet wonder of science. Before we continue, I'd love to know where you're listening from. Tell me your country, your city, and what time it is there right now. I always enjoy seeing how far these quiet science journeys travel around the world. And wherever you are, whatever time it is, the light around you is doing something incredible. It is moving. It is always moving. Light never stops. From the moment a tiny particle of light, called a photon, is born inside a star, it begins a journey that might last for millions or even billions of years. It travels across the emptiness of space without rest, without pause, until it finally reaches something that stops it. He thought that our eyes sent out some kind of invisible ray that reached out and touched objects, and that is how we saw them. Like an invisible finger feeling the shapes of things in the world. Sometimes it stops on the surface of a planet. Sometimes it stops inside your eye. And in that very moment, when light touches your eye, you see. That is what we are going to explore together. We will start at the very beginning with a simple question. What is light? If you look around you right now, you can probably see many things. Perhaps you see a window, a wall, a book, or the soft glow of a lamp. You can see these things because light is bouncing off them and entering your eyes. But what is that light? For thousands of years, human beings wondered about that exact question. The ancient Greeks, who lived more than 2,000 years ago, thought about light very carefully. They noticed that when you look at a tree, something must be traveling from the tree to your eyes. But how did that work? One famous Greek philosopher named Empedocles had an interesting idea. He thought that our eyes sent out some kind of invisible ray that reached out and touched objects, and that is how we saw them, like an invisible finger feeling the shapes of things in the world. Another Greek philosopher named Aristotle disagreed. He believed that light was not something our eyes sent out. Instead, he thought that light was something that traveled from the object to our eyes. He noticed that if you light a candle in a dark room, the light spreads out in all directions. That meant the light was coming from the candle, not from your eyes. Aristotle was closer to the truth, but it would take many hundreds of years before anyone really understood what light actually was. The ancient Greeks also thought about something very interesting. They noticed that light travels very fast. If you see a lightning flash in the sky and then hear the thunder a few seconds later, you know that light must travel much faster than sound. Sound takes time to reach your ears, but light seems to arrive instantly. The great philosopher Aristotle wondered if light traveled at an infinite speed. Infinite means without any limit at all. It means that light could go anywhere in no time at all. But was that true? For hundreds of years, no one really knew. Then, in the 11th century, a brilliant scientist named Ibn al-Haytham appeared. He was born in what is now Iraq, and he is sometimes called the father of modern optics. Optics is the study of light and how it behaves. Ibn al-Haytham did something very important. Instead of just thinking about light, fact, he experimented with it. He used dark rooms, which he called camera obscura. That is a Latin phrase that means dark chamber. He made a small hole in the wall of a dark room, and he watched how light from outside entered through that hole and created an image on the opposite wall. He noticed that the image was upside down. That told him something very important. Light travels in straight lines. If you stand outside in the sunshine and put your hand in front of a wall, you will see a shadow. That shadow is evidence that light travels in straight lines. The light from the sun cannot bend around your hand. It is blocked, and a shadow appears. Ibn al-Haytham was one of the first people to really prove that light is a physical thing that travels from an object to our eyes. He also proved that light does not travel infinitely fast. He realized that light has a finite speed. That means it is not instantaneous. It takes time to get from one place to another, even if that time is very, very short. But he was not able to measure exactly how fast light travels. For that, the world had to wait many more centuries. Now let us think about something amazing. Every single thing you see in your everyday life, every tree, every person, every cloud, every star, you see because light has traveled from that thing to your eyes. But how does light travel? What is it made of? To understand that, we need to think about a very important idea. Light is a type of wave. You have probably seen waves before. If you throw a pebble into a calm pond, you will see ripples spread out across the water. Those ripples are waves. They carry energy from the pebble to the edges of the pond. Sound is also a wave. When someone speaks, their voice makes the air vibrate. Those vibrations travel through the air as sound waves and enter your ears. Light is also a wave, but it is a very special kind of wave. It is an electromagnetic wave. That is a big word, but we can break it down. Electromagnetic means that light is made of two things working together. One part is an electric field, and the other part is a magnetic field. These two fields are always connected to each other. Electric fields are all around us. You experience electricity every time you turn on a light switch. Magnetic fields are also all around us. You experience magnetism when you play with a magnet. Light is a wave that is made of these two fields, dancing together, moving through space. But here is the thing that makes light so special. Light waves do not need anything to travel through. Sound waves need air. If you were in outer space and someone tried to talk to you, you would not hear them because there is no air for the sound waves to travel through. Water waves need water. But light waves are different. Light waves can travel through empty space. They can travel through the perfect emptiness between planets and stars. They can travel through the vacuum of space. That is one of the most important things about light. It does not need a medium. A medium is just a word for something that waves travel through. Light travels through the vacuum of space at a speed that we call the speed of light. And that speed is the most important number in all of physics. But we have not yet reached that part of our story. First, we need to understand more about what light is made of. For a very long time, scientists debated whether light was a wave or a particle. A particle is a tiny piece of matter. Think of grains of sand. Each grain is a particle. It is a small, solid piece of stuff. Sir Isaac Newton, the famous English scientist from the 1600s, believed that light was made of particles. He called them corpuscles. Newton was one of the greatest scientists who ever lived. He discovered many important laws about gravity and motion. His ideas about light were very influential. He believed that light was a stream of tiny particles shooting out from a source, like a candle or the sun. He thought that these particles travelled in straight lines, which explained why shadows are sharp. Newton's particle theory of light was very popular for a long time. But there was another scientist who had a different idea. His name was Christian Huygens, and he was from the Netherlands. Huygens believed that light was a wave. He noticed that when light passes through a small hole, it spreads out a little bit, like ripples in a pond. If light were made of particles, it would not spread out that way. It would just go straight through. Huygens also noticed something called interference. Interference is what happens when two waves meet each other. If you have ever seen two sets of ripples in a pond meet, you have seen interference. Sometimes they add together and make bigger ripples. Sometimes they cancel each other out and make flat water. This is something that only waves can do. Particles do not interfere with each other like that. Huygens was correct about many things, but during his lifetime, Newton was more famous and more respected. So most people believed that light was made of particles. It would take more than 100 years before scientists had the right tools and ideas to prove that Huygens was right. But as we will discover later, the story does not end there, because light is both a wave and a particle. It is something we call wave-particle duality. That means light acts like a wave in some situations and like a particle in other situations. It is one of the strangest and most wonderful things in all of science. But let us not rush ahead. We are going to take our time. Let us think about the speed of light again. We said earlier that light travels very fast. But how fast is it exactly? If you look at a light bulb, the light seems to reach your eyes instantly. But it is not instant. It just seems that way because light travels so fast. To measure the speed of light, scientists had to come up with clever experiments. The first person to seriously try to measure the speed of light was a scientist named Galileo Galilei. Galileo is one of the most famous scientists in history. He was born in Italy in 1564 and made many important discoveries about motion, gravity, and the planets. Galileo tried to measure the speed of light using a very simple method. He and an assistant went to two hilltops that were separated by a distance. Galileo had a lantern that he could cover and uncover. He would uncover his lantern, and the assistant would see the light, and then uncover his own lantern. Galileo would time how long it took between his uncovering and the assistant's response. This was a clever idea, but it did not work. The speed of light is so fast that the time it took to travel between the two hilltops was much too short for Galileo to measure. He concluded that light must be incredibly fast, and maybe even instantaneous. But Galileo was one of the first people to try to measure the speed of light in a scientific way. He showed that this was an important question, even if he could not answer it. About 50 years later, a Danish astronomer named Ole Romer made the first real measurement of the speed of light. Romer was looking at Jupiter, one of the planets in our solar system. Jupiter has moons, just like Earth has one moon. But Jupiter has many moons. One of these moons is called Io. Romer was making careful observations of Io. He noticed that Io would disappear behind Jupiter at regular intervals. It would be eclipsed by the planet. But he also noticed something strange. When Earth was moving away from Jupiter, the eclipses happened a little bit later than expected. When Earth was moving toward Jupiter, the eclipses happened a little bit earlier than expected. Romer realized that this was because of the speed of light. When Earth and Jupiter were farther apart, the light from Io had to travel farther to reach Earth, so it took more time. When Earth and Jupiter were closer together, the light had less distance to travel, so it arrived sooner. This was brilliant reasoning. Romer used his observations to estimate the speed of light. He did not get the exact number that we know today, but he was very close. He proved that light has a finite speed. He proved that it is not infinite. This was a huge breakthrough. For the first time, humans had real evidence that light takes time to travel. Later scientists would build on Romer's work and get more and more accurate measurements. In the 1800s, a French scientist named Armand Fizeau designed a very clever experiment. He used a spinning wheel with teeth and a mirror. He would shine a beam of light through one of the gaps between the teeth, and the light would travel to a mirror and reflect back. If the wheel was spinning slowly, the light would come back through the same gap. But if the wheel was spinning fast enough, the light would come back when a tooth was in the way. The tooth would block the light. Fizeau measured the speed of the wheel and the distance the light travelled. From that, he calculated the speed of light. His measurement was very accurate. He showed that light travels at about 300 million meters per second. This is a huge number. Let us put it in perspective. If you could travel at the speed of light, you could go around the entire Earth about 7.5 times in just 1 second. That is incredibly fast. But it is not infinite. It is a finite number. And that finite number, that exact speed, is one of the most important constants in the universe. A constant is something that always stays the same. The speed of light in a vacuum is always the same. It does not matter if you are moving toward the light or away from it. It does not matter if the light is coming from a star that is moving or from a flashlight in your hand. The speed of light is always the same. This might sound simple, but it is actually very strange. Think about a car. If a car is driving at 50 kilometers per hour and you are standing on the side of the road, you measure the car's speed as 50 kilometers per hour. But if you are in another car driving at 30 kilometers per hour in the same direction, the first car appears to be moving at only 20 kilometers per hour relative to you. Speeds depend on your point of view, but light does not work that way. No matter how fast you are moving, you will always measure the speed of light as the same exact number. This is one of the most surprising discoveries in all of science. It was a scientist named Albert Einstein who figured out what this means. Einstein was born in Germany in 1879, and he is one of the most famous scientists who ever lived. He developed two incredible theories. One is called special relativity, and the other is called general relativity. These are big words, but we are going to explore them slowly and gently. Special relativity is about light and time and space. When Einstein realized that the speed of light is always the same, he started thinking about what that meant for the rest of physics. He realized that if the speed of light is always the same, then something else must change. That something is time itself. Time is not the same everywhere in the universe. Time flows differently depending on how fast you are moving. If you travel very fast, close to the speed of light, time moves slower for you than for someone who is standing still. This is called time dilation. Dilation is just a word that means stretching. Time stretches. So if you were on a spaceship traveling at nearly the speed of light, time would pass more slowly for you than for people back on Earth. If you left Earth on such a spaceship and traveled for a year, when you came back, you might find that many years had passed on Earth. Your friends and family might be much older than you. This sounds like science fiction, but it is real. It has been proven by experiments. Scientists have used extremely accurate clocks on airplanes and satellites. They have compared these clocks to clocks on the ground. The clocks on the moving airplanes and satellites run just a little bit slower. The difference is tiny, but it is real. And it happens because the speed of light is always the same. That constant speed forces time and space to bend and stretch. Time is not a single universal thing that ticks the same for everyone. Time is personal. It depends on where you are and how fast you are moving. This is a very deep idea. Let us take a moment to let it sink in. We are so used to thinking that a minute is a minute, an hour is an hour, a day is a day. We think time is the same for everyone, but it is not. The universe is much stranger than we usually imagine, and it all comes back to light. The speed of light does not just change time, it also changes space. When something moves very fast, it also gets shorter. This is called length contraction. If you were moving at nearly the speed of light, you would measure the distance in front of you as being shorter than someone who is standing still would measure it. Again, this is real. It has been proven by experiments. Space and time are connected. They are part of the same thing. We call it space-time. Space-time is a fabric, like a blanket, that covers the entire universe. Matter and energy can bend this fabric. A heavy object, like a star or a planet, bends space-time around it. This bending is what we experience as gravity. That is the idea behind Einstein's general relativity. Gravity is not a force that pulls things together, like Newton thought. Gravity is the bending of space-time. Light is affected by this bending. When light passes near a massive object, like a star or a black hole, its path is curved. We call this gravitational lensing. It is like looking through a giant magnifying glass made of gravity. Black holes are the most extreme example of this. A black hole is an object so dense that its gravity bends space-time completely. Not even light can escape from a black hole. If light gets too close, it is trapped. We cannot see a black hole directly because no light escapes from it, but we can see the effects of a black hole on the light around it. We can see matter swirling around a black hole, getting hotter and hotter and glowing brightly before it falls in. And we can see light bending around a black hole, creating weird and wonderful effects. So light is not just something we see with our eyes. Light is a fundamental part of how the universe works. It connects us to the cosmos. Every time you look up at the night sky, you are looking at light that has traveled across space. And the light from very distant stars and galaxies has been traveling for millions or billions of years. So when you look at those distant objects, you are not seeing them as they are today. You are seeing them as they were when the light left them. You are looking into the past. This is one of the most profound ideas in all of science. The light from a star that is 100 light years away has been traveling for 100 years. A light year is a unit of distance. It is the distance that light travels in 1 year. Light travels about 300 million meters every second. So in 1 year, it travels about 9.46 trillion kilometers. That is a huge distance. A light year is a very big number. So when we say that a star is 100 light years away, we mean that its light takes 100 years to reach us. When we look at that star, we see it as it was 100 years ago. We are seeing the past. This is true for everything you see. Even the light from the moon takes about 1.3 seconds to reach Earth. So you are always seeing the moon as it was 1.3 seconds ago. The light from the sun takes about 8 minutes to reach us. So when you look at the sun, you see it as it was 8 minutes ago. If the sun suddenly disappeared, we would not know it for 8 minutes. The light would stop coming and the sky would go dark. But it would take 8 minutes for that information to reach us. This is a powerful reminder that we are always living in the past. We see the past in the light around us. And when we look deep into the universe, we can see back to the very beginning of time. This is how we know about the early universe. There is a faint glow of light that fills all of space. It is called the cosmic microwave background radiation. It is the leftover light from the Big Bang. The Big Bang is the name for the beginning of the universe, about 13.8 billion years ago. At that time, the universe was incredibly hot and dense. It was a soup of energy and particles. As the universe expanded and cooled, light was able to travel freely. That ancient light is still traveling through space today. It is very faint and very cold now. But it is everywhere. We can detect it with special instruments. And it tells us about the universe when it was only about 380,000 years old. That is very young compared to its age now. So light acts as a time machine. It lets us travel back in time. When we look at the cosmic microwave background, we are looking at the universe when it was a fraction of its current age. This is one of the greatest achievements of modern science. we can see the infancy of the universe, and we can watch it evolve and change over billions of years. We can see galaxies form and stars ignite. We can see the large-scale structure of the universe, and we can trace our own history back to the beginning. It is all because of light, but we are still only at the beginning of our journey. We have talked about what light is, how it was discovered, and why its speed is so important. Now let us explore some of the amazing things that light can do. Let us think about color. What is color really? Color is just our brain's way of interpreting different wavelengths of light. We mentioned earlier that light is a wave. Waves have a property called wavelength. Wavelength is the distance between two peaks of the wave. Some light waves have very short wavelengths, and some have very long wavelengths. The human eye can see only a very small range of wavelengths. This range is what we call visible light. Within this range, different wavelengths correspond to different colors. Red light has a long wavelength. Violet light has a short wavelength. The colors of the rainbow are just different wavelengths of light. Red, orange, yellow, green, blue, indigo, and violet. Each one is a different wavelength. You can see a rainbow when sunlight passes through water droplets in the air. The water droplets bend the light. This bending is called refraction. Refraction is what happens when light passes from one medium to another, like from air to water. Light slows down when it enters a denser medium, like water or glass. This slowing down causes the light to change direction. It bends. Different wavelengths of light bend by different amounts. Blue light bends more than red light, so when sunlight passes through a raindrop, the different colors are separated. They spread out, and you see a rainbow. The sky is blue because of something similar. Sunlight is made of all colors. When sunlight enters Earth's atmosphere, it collides with molecules in the air, like nitrogen and oxygen. Blue light has a shorter wavelength and is scattered more than red light. Scattering means the light is bounced in many directions, so blue light is scattered all across the sky. That is why the sky looks blue. At sunset, the sun is lower in the sky. The light has to travel through more of the atmosphere. More of the blue light is scattered away, and the red and orange light passes through. That is why sunsets are red and orange. It is all about how light interacts with the air. Color is such an important part of our lives. It gives the world beauty and variety. And it all comes from the way light waves interact with matter. Now let us think about invisible light. Visible light is just a tiny part of the electromagnetic spectrum. The electromagnetic spectrum is the full range of electromagnetic waves. It includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Each of these is a type of light. They are all electromagnetic waves. They just have different wavelengths and frequencies. Radio waves have very long wavelengths. They are the longest waves in the spectrum. They are used to transmit radio and television signals. Microwaves have shorter wavelengths than radio waves. They are used in microwave ovens and in radar. They are also used in communication like Wi-Fi. Infrared has shorter wavelengths than microwaves. We cannot see infrared light, but we can feel it as heat. Any object that is warm gives off infrared light. Our bodies give off infrared light. That is how night vision cameras can see in the dark. They detect the infrared light that our bodies emit. Visible light comes next. It is the very small range that our eyes can see. Then comes ultraviolet light. Ultraviolet is the light that gives you a sunburn. It has shorter wavelengths than visible light. It has enough energy to damage your skin cells. Beyond ultraviolet are X-rays. X-rays have very short wavelengths and high energy. They can pass through soft tissue, but they are absorbed by bones. That is why doctors use X-rays to see inside your body. The X-rays pass through your skin and muscles, but they are stopped by your bones. The image that forms on the X-ray plate shows the bones. Finally, there are gamma rays. Gamma rays have the shortest wavelengths and the highest energy. They are produced by very energetic events in the universe like supernovas and black holes. They are also produced by radioactive decay. Gamma rays are very powerful and can be dangerous. But they also have medical uses, like in cancer treatment. The entire electromagnetic spectrum is a wonderful range of light. It is all the same thing, just at different wavelengths, and it all travels at the same speed, the speed of light. So when you use your phone, you are using radio waves and microwaves. When you feel the warmth of the sun, you are feeling infrared light. When you get an X-ray, you are using X-rays. And when you see a rainbow, you are seeing visible light. Light is everywhere. It is all around us. It is in our homes, in our cities, in our bodies, and in the far reaches of the universe. Now let us think about how we use light. One of the most important inventions that uses light is the laser. Laser stands for light amplification by stimulated emission of radiation. It is a device that produces a very narrow, very powerful beam of light. The light in a laser is all the same wavelength and all in phase. In phase means the waves are perfectly aligned. This makes laser light very different from ordinary light. Ordinary light, like from a light bulb, is made of many wavelengths and many phases. It spreads out in all directions. But laser light is highly concentrated. It can travel very long distances without spreading out. Laser light is used in many ways. It is used in barcode scanners at the grocery store. It is used in CD and DVD players. It is used in surgery to cut tissue very precisely. It is used in communication to send information through fiber optic cables. Fiber optic cables are thin strands of glass or plastic. They carry light over long distances. The light bounces along the inside of the fiber and it does not escape. This allows us to send huge amounts of information quickly. The internet is built on fiber optics. Without light, the modern world as we know it would not exist. But the uses of light go much further. Cameras use light to capture images. A camera has a lens that focuses light onto a sensor. The sensor records the light and creates a digital image. The first cameras were very simple. They used a pinhole to let light in, and the light created an image on a piece of film. Now cameras are incredibly advanced. They can capture billions of pixels of information. Telescopes are like cameras that look at the sky. They gather light from stars and galaxies and focus it to create images. The bigger the telescope, the more light it can gather. And the more light it gathers, the fainter the objects it can see. There are telescopes all over the world. There are also telescopes in space. The Hubble Space Telescope is one of the most famous. It has taken amazing pictures of the universe. It has shown us galaxies forming, stars being born, and nebulae glowing. The James Webb Space Telescope is even more powerful. It can see further into the past than any other telescope. It is helping us understand the earliest moments of the universe. Microscopes are the opposite of telescopes. They use light to look at very tiny things. A microscope magnifies small objects so we can see them. It lets us see cells, bacteria, and other tiny organisms. Without microscopes, we would not know about germs. We would not understand the building blocks of life. Microscopes have transformed medicine and biology. All of these instruments, from telescopes to microscopes, rely on the properties of light. They rely on reflection, refraction, and focusing. Reflection is when light bounces off a surface. You see your reflection in a mirror because light bounces off the mirror and enters your eyes. Refraction is when light bends as it passes from one material to another. Lenses use refraction to focus light. A magnifying glass uses a curved piece of glass. Light bends as it passes through the glass, and it focuses to a point. That point is where the light is concentrated. That is how a magnifying glass can set a piece of paper on fire. It concentrates the sunlight onto a small spot. The same principles are used in telescopes and microscopes. The entire field of optics is about understanding and using light. But light is not just about seeing. It is also about understanding the universe on a deeper level. There is a technique called spectroscopy. Spectroscopy is the study of the spectrum of light. We talked earlier about how a prism separates light into its colors. That is a spectrum. But spectroscopy goes much deeper. When scientists look at the light from a star, they split it into a spectrum. They look at the lines in that spectrum. Those lines are like fingerprints. They tell you what elements are in the star. Each element emits or absorbs light at specific wavelengths. So by looking at the lines in the spectrum, scientists can identify the elements in the star. They can see hydrogen, helium, oxygen, iron, and all the other elements. This is how we know what stars are made of. We cannot travel to a star and bring back a sample. We cannot touch it or measure it directly. But we can analyze its light. The light carries information about the star. This is one of the most powerful tools in astronomy. Every beam of light is like a message in a bottle. It carries information from distant places. And we are learning to read that message. Another way we use light is to detect planets around other stars. These are called exoplanets. They are planets that orbit stars outside our solar system. It is very difficult to see an exoplanet directly. They are very small and very faint compared to their parent star. It is like trying to see a candle next to a giant spotlight. But we can detect exoplanets using light. One method is the transit method. When an exoplanet passes between its star and us, it blocks a tiny bit of the starlight. That small dimming tells us a planet is there. We can even learn something about the planet's atmosphere. As the light from the star passes through the planet's atmosphere, the atmosphere absorbs some of the light. By looking at the spectrum, we can tell what gases are in the atmosphere. We can find oxygen, water, and other molecules. This is how scientists are looking for signs of life on other planets. We are looking for biosignatures, which are signs of life in the light. This is a very exciting area of science. The Doppler effect is another important concept. The Doppler effect happens when a source of waves is moving. You have probably experienced the Doppler effect with sound. When an ambulance with a siren passes by, the pitch of the siren changes. It is higher as it comes toward you and lower as it moves away. This happens because the sound waves are compressed or stretched. The same thing happens with light. When a star is moving toward us, its light is compressed. The wavelengths get shorter and the light shifts toward the blue end of the spectrum. This is called blue shift. When a star is moving away from us, its light is stretched. The wavelengths get longer and the light shifts toward the red end of the spectrum. This is called redshift. Edwin Hubble was an astronomer who studied the light from distant galaxies. He noticed that almost all galaxies are redshifted. This means they are moving away from us. In fact, the farther away a galaxy is, the faster it is moving away from us. This was a huge discovery. It showed that the universe is expanding. Everything in the universe is moving away from everything else. It is like a loaf of raisin bread rising in the oven. The raisins all move apart from each other as the bread expands. The universe is doing the same thing. It is expanding. This expansion started with the Big Bang, and it is still happening today. So light tells us about the expansion of the universe. It tells us about the beginning and the evolution of everything. But there is more to the story. Dark matter is a mystery that light is helping us understand. Dark matter is a type of matter that we cannot see. It does not emit, absorb, or reflect light. But we know it is there because of its gravity. It affects how galaxies rotate and how light travels through space. Gravitational lensing, which we discussed earlier, is a powerful tool for studying dark matter. By observing how light is bent by the gravity of dark matter, scientists can map where dark matter is. It is a way of seeing the invisible. We cannot see dark matter directly, but we can see its shadow in the light. This is just another way that light reveals the secrets of the universe. We are living in a golden age of discovery. Our understanding of light has led to technologies that were unimaginable to our ancestors. But there is still so much to learn. There are still great mysteries. One of the deepest mysteries is the nature of quantum mechanics. Quantum mechanics is the science of the very small, of atoms and particles. Light is a quantum object. It has properties of both waves and particles. A photon is a quantum of light. It is the smallest possible amount of light. A photon has energy. The energy of the photon is directly related to its wavelength. Photons with shorter wavelengths, like gamma rays, have more energy. Photons with longer wavelengths, like radio waves, have less energy. This is why ultraviolet light can give you a sunburn. Its photons have enough energy to damage your skin cells. Quantum electrodynamics is a theory that explains how light interacts with matter. It is one of the most accurate theories in all of physics. It describes how photons interact with electrons and other charged particles. It is a beautiful and complex theory. But even with all these discoveries, there are still questions that we cannot answer. Why does light travel at exactly the speed that it does? Why does the universe have this particular constant? Some scientists think that the speed of light is connected to the fundamental structure of the universe. It might be a property of space-time itself, but no one knows for sure. It is a deep mystery, and it is okay not to have all the answers. Science is a journey, not a destination. We are always learning new things and asking new questions, and that journey is beautiful. So let us reflect on everything we have talked about. We began with a simple question: what is light? And we found that light is an electromagnetic wave. It is a photon. It is both a particle and a wave. It travels at a constant speed. That speed is one of the most important numbers in physics. It affects time and space. It connects us to the cosmos. It lets us see the past. It is the messenger of the universe. Light is the reason we can see the stars. It is the reason we can understand the world around us. It is the reason we can connect with each other through technology. When you look at your phone, you are using light. When you see a beautiful sunset, you are seeing light. When you look up at the night sky, you are looking at ancient light. Light is a thread that weaves through everything. It is in the smallest atom and in the largest galaxy. It is in your eyes and in the depths of space. It is the story of the universe, and we are part of that story. We are made of the same stuff as the stars, and we are illuminated by the same light. So the next time you see a beam of light coming through a window, take a moment. Think about where that light has been. It might have come from the sun. It might have traveled 8 minutes across space. It might have started its journey millions of years ago in the heart of a distant star, and now it is here. It is touching your face. It is filling your eyes. It is connecting you to the entire universe. That is the magic of light, and that is the story of its speed. Thank you for spending this time with me. Thank you for taking this quiet journey through the science of light. I hope you feel a little more peaceful and a little more connected to the wonders of the universe. May your dreams be filled with gentle starlight, and may you find rest in the beauty of the cosmos. If you enjoy these relaxing science journeys, you might like to subscribe. There are many more stories to tell. But for now, it is time to rest. Good night.